Hello, this is going to be the first one on communications, data communications. So, the first one then is communication methods. So, make sure you've got this is the PowerPoint. You should have that. You should have some questions here as well. And you should also have all the other stuff as well. So, we're doing topologies, client server, peer to peer, pretty easy, wireless networking. Checking for errors as well, and there's some programming to do as well. So there's quite a lot on this one. So let's make a start. So, right, okay, first one then is this PowerPoint here. Now this will take a while, but shouldn't be too bad. Right, okay. So those are what we're going to be covering. I say I'm not going to read them to you because you'll get there eventually. Right, okay, first one is serial and parallel. Now, serial and parallel, very high transfer rates can be achieved with serial. So the idea with serial is that you've got a single wire and multiple bits sent one after the other. Okay. Now, parallel, you would think, is better. Okay. So what you're doing is you're sending down multiple wires, bits simultaneously. So you're sending all of that in one go, then that in one go, then that in one go, depending on which way it's going. But there are problems with parallel. Okay. Now here we go. Here's another description. Sending banana. You're going to sending one a B, then an A, and so forth. Whereas that with parallel, you can send it all in one go. But the problem is, over long distances, you get what's called skew. You see that the bits will become unsynchronized. So that means you have to slow it down in order to actually, so if you imagine you have a line going down here, then a line going down here before you can send the next one, because obviously if we're reading it along there and along there, we're going to miss bits. All right. So for longer distance, serial is actually better, it's faster, and also you can get interference can occur at high frequency with parallel. You get something called crosstalk as well. Right. So those are the main differences between the two. And you know, parallel I don't know, if you were in class, I would show you that, you know, we used to use parallel connectors or PATA for hard disks. Now we use SATA instead, much thinner cable, much easier to connect, and so forth. So where you will see parallel still is on the buses. Blakey. Right. So the data bus, address bus, and control bus. Right. Okay. Now bitrate and baud rate. Now the speed in which is measured in bits per second. The baud rate is different. It's the rate in which the signal changes. Now you have to remember that. Now the bit rate of a channel is the baud rate times the number of bits per signal. Now, this is baud rate. I mean, it seems a bit nebulous really for our syllabus, but essentially what you can do, and this isn't how it generally is. The only time you ever see baud rate, as I remember, was when we were using old dial-up, and it would tell you the baud rate. Now the baud rate was usually higher than the bit rate, okay, because it used to, you know, take more than one change of signal to represent a bit. Okay, but this is the classic example, and this is in the exam board here. What they can do though is you can represent more than one bit, or two bits in this case, for each signal level. All right, so the voltage 5 can represent 1 0, 2.5 volts is 0 1. Now you can represent, so if I want to represent 1101, I would do 7.5 1101, wasn't it? And then followed by that. So you can represent any bit. But what we're saying is though that each signal change here represents more than one bit. So one baud equals 2 bits per second, 2 BPS. Now the bit rate is always measured in bits per second. So when you're talking about your download speed from your internet provider, it's always in bits per second rather than bytes per second. Now your bandwidth is the range of frequencies that a medium can transmit. So a high bandwidth, such as fiber optic, can actually represent or transmit a very wide range of frequencies, whereas a string with yogurt pots on the end, if you've ever done that, has very low bandwidth. All right. So the greater the bandwidth, the greater the potential bit rate. Okay. So it doesn't mean you're definitely going to have a high bit rate, but you've got the potential for a much higher bit rate. Now latency, that's the time delay occurs when a component in the system is responding to an instruction. So a good example of that, we're all aware of what's called lag in games. So if you ping google.co.uk here, you get a result coming back. Okay, so obviously the longer it takes to get back, the slower the latency. Now latency can be caused by two things, either the network being slow or the actual machine itself being slow to respond. All right, so it's not just the networking part of it. Now if the machine's overloaded, then that's it. Now parity, this is a way of checking to see if what you're sending is received. Okay, now it's very simple, it's widely used, it's not that effective, but it's simple. It has low overhead costs in terms of processing. Now going back to ASCII, the original ASCII codes were obviously using 8 bits, but actually they only used 7 bits to represent, so that would be 127 codes. So we could use the 8th bit there to represent our parity bit. Okay. Now, so what we do is we just make the most significant bit, or the parity bit, either a 1 or a 0, to make the number of ones in our 7 bits overall odd or even. It's easy to show an example here. Right, so on this one here, so we've got 7 bits, and then we're going to be using odd parity. So we want to make our parity bit. Now I should really put this here. So we've got, count up the number of bits, 1, 2, 3. So we've got 3, so the parity bit would be a 0. So on this one here, add up the number of ones, 1, 2, 3, 4, 5. It's already odd, so we'll make the parity bit a 0 there. Now we're using even parity, so 1, 2, 3, 4, 5. So that would have to be a 1 to make it even. And then do the same here, 1, 2, 3, 4, 5. So it looks like it's another 1 there. The parity bit would normally go in that position there. Right, now the synchronous transmission, this is another thing that would be easy probably to explain in class, but okay, we'll give it a go. Now synchronous means occurring at the same time or having the same speed. Okay. Now when we are communicating with another device, we have to be synchronized with them. All right, so if you think about it, when we're sending data, we're going send, 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 bit, 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 and the receiver have to be in the same synchronization so it can receive our bits. It doesn't want to be out of sync. It doesn't want to be trying to read it faster than we're sending it or slower than we're sending it. So what we use is a clock, okay, that both the sender and receiver will synchronize on, and that's called synchronous transmission. Okay. Now asynchronous transmission is slightly different, is the fact that the only in synchronization for the duration of the sending of a byte of data. Okay, and then they don't have to be. Okay, so as it says, that only synchronizes for the duration sent by sending additional bits in which will start and stop bits, whereas our synchronous here is in constant, it's always in synchronization. Okay. So how does it do that? Well, we want to send the character code R here. All right, so there's 7 bits to do that. That's the ASCII code for R. So what we do is we have a start bit. Now the start bit will wake up the receiver and go, right, okay, I've got something coming. So I start my clock now, and then I go tick, 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 tick as I read it off at the same speed that the sender was sending it. Then we have a parity bit, so we read the parity bit, and then we have a stop bit. All right, so the stop bit is there to allow the receiver to read and process that before the next bit. Now imagine we're pressing keys here on a keyboard or something like that. Okay, now the start and the stop bit must both be different. So it doesn't matter if that's a 0, that would have to be a 1 to make it different, because the next bit after that could be a start bit. Okay, so we want to be able to differentiate between the two. All right, so that's essentially it. Now this little bit down here, so we have a start, the data, the stop, start, data, stop, and then so forth. So what this allows us to do then, the start bit arrives, right, we start synchronizing and then reading the 7 bits plus the parity bit. Then we have a stop bit to be able to process it, and then we wait again. And there may not be one for ages. So the idea is that it's not continuous traffic or continuous data. It's going to occur intermittently, just like keyboard strokes or something like that. Okay, now I'm not going to go through that. I basically just explained that. Right, protocol. Protocol is a set of rules relating to communication between two devices. There are many protocols. TCP/IP, probably the most famous one. Transmission Control Protocol, Internet Protocol. Now the idea is for this is so we can allow different people who make equipment connect with other people. So as long as we're all using the same protocol, it all works. Like, for instance, USB is essentially a protocol. So if I design something, a new device, and I go, right, it's USB 3, that's great. I mean, everyone else can connect to it. All right, but it's also to do with networking as well. So what can be there? Well, we have physical connections. So when you define, if I want to create a new device, USB 3, I can look up what are the physical dimensions for that. The cabling required, the transmission speeds, the data format, that's really important that we're sending across. So for instance, if I want to connect to the internet, then I have to use the TCP/IP, and I can look up the kind of format for that. Error detection and correction, which we'll look at in more detail later. Right, there's some exercises there which you've got. Whoops. Now on that bit there, the start and stop bit, just make sure they're different, and the parity bit's just worked out from the data bits, not including the start and the stop bit. Okay, so the rest of it is really just kind of looking over the notes there. Okay, right, and there's another one there and another one there, but you've got that here. All right, okay, that is the first one done.